হ্যালো এভরিওয়ান। তো এখন আমরা যে প্রবলেমটা দেখব এটা হচ্ছে অর্ডারিং ট্রি। সো একটু প্রবলেম স্টেটমেন্টটা দেখে আসি যে এখানে কি বলছে। ইউ আর গিভেন অ্যান অ্যারে এ অফ সাইজ n which is নন ডিক্রিজিং অর্ডার। তার মানে আমাকে একটা n সাইজের অ্যারে দেয়া আছে which is sorted in non decreasing order. Find out any order of these n integers such that if this integer are inserted into a binary search tree one by one, the height of the resulting BST is minimized, which means আমাদের এই অ্যারেকে এমন ভাবে অর্ডার করতে হবে so that এই অর্ডারিং থেকে যদি কোনো বিএসটি বানানো হয় ওই বিএসটিটার হাইট মিনিমাম হবে। So we need to order this array in that manner, specific manner. So how we can solve this problem? So let's see an example. So let's say we have an array which contains 1, 2, 3, 4 and 5. So how we can construct a BST from this array? So one possible construction could be this, because every node in this tree has lesser than 1, lesser than 2 subtree or lesser than 2 childs. So as it it's written here that binary search tree is a binary tree in which each node has at most 2 children. So yeah, it's a valid binary tree because it has less than 2 or at most 2. It can have at most 2 children, but we have lesser than 2, so it's a valid binary tree. Okay, but the problem with this tree is its height is larger. For example, its height is 1, 2, 3 and 4, right? We need to construct a tree in a way such that the height is minimized. So now if we look at the right hand side in this specific tree, we can see this is our root node, because in a binary tree the root node is basically the center of the tree, and the left subpart of the tree contains all the element from the left side of the array, and right part of the tree will contain all the element from the right part of the array. So thus we can construct a node of this binary tree. Now for the left subtree we have the similar problem. Like if we have now this part of this array and we need to this node construct this node. So what we can do is simply perform some recursion and do the same for this left subtree. Similarly the same for the child of this tree, the right part of this tree, and when we are done with this part we'll return to our node, root node, and then do the similar for the right part of this tree. And that's how we basically uh, construct our mean height BST. So let's see how we can do that. So first of all, let's copy this array. Okay, so let's copy this array here. Now if we look at this array and if we try to create the root of our node, we can say this root will be the middle of this array, because this array is sorted, and the middle element should be the root of the binary tree, because all the left childs are lesser than 3, all the right childs are larger than 3, which satisfy the property of binary search tree. Now we have the similar problem for this left part of the tree, right? So what we can do is we'll simply create a pointer here, which is I, and create another pointer here, which is j. So we will simply get the mid and set it as our root node. Then our task is to just do the same thing for the left subtree. For the left part here, our I is here and our j is here. Now if we calculate the mid of this part, which is 0 plus 1 divided by 2, and we will get 0. So our mid will be pointing to this index as well. So here is our mid. Now what we will do, we will generate another root node for this subtree, and we'll simply do the same thing for the left part of this tree. So we'll move this j to this part, but now you can see j is lesser than I, which means j is left to I, and we have no nodes here. If this condition occur, we can simply return, because this is just my base case. Okay, so we return this and create a connection with 3. Okay, so now we have, basically we are not creating this connection here, we are simply return something none from there and create a connection. Now for the right part, which is 2, our I would be, let's remove all this thing, our I would be here, our j will also be here, and as a result our m will also be here. So the right part of this root node should be 2, and after 2 we will again move this j pointer to here, and now we have nothing in the left, because this is already our root node and this is also already our root node. So as j crosses I, so that's why we can say 2 is basically a leaf node. So now we return this to the 1 and we will get a connection like this. After that, when we are done with this, we return this 1 to 3 and get a connection like this. So similarly, we'll do the same thing for the left part, as this simulation is becoming a bit clustered. I just remove all these things. Okay. So now what we will do, we'll do the same thing for the right part. And here my left is this 4 and my right is 5. So let's make a pointer. This is my I, here is my j. What will be my middle? M equals to 3 plus 4 float division 2, which is 7, float division by 2, which is 3. So our middle will be here. and this is gonna be our root of the next node. So after making it a node root, we simply move our right pointer. So let's move our right pointer to the left, and now j crosses I. So 4 will return to the, there will be none, and this will return to the 4. Okay, now we have similarly 5 left. So 5 will be the next root, and there will be no child of 5. So 5 will simply return to 4, and 4 will again return to 3. And this is how we construct the tree. And if we make it ordering, we can say this is 0, this is 1, 2, 3, and 4. So our answer should be look like 3, 1, 2, 4, and 5. Okay, so that's it. Thank you.